There we go. All right, so just a couple of things to get us right off the bat here, thinking about things. Pretty crazy to think that we are we're right here already. It's already November 16th, which I mean it's flown by, but yet it's kind of it's been a struggle too. I know. So here we are, and you guys have done so well so far to get to this point. I've the latest rounds of sketch notes and things should all be graded, and you should be able to see those in the comments and things like that. If you still need to get in a few of your sketch notes, that's fine. I'll grade them. That's great. Just do what you can just to stay as much as caught up as possible. All right. But just to give you a heads up, so next week, right? No classes at all next week for us. It's those non-instructional days / Thanksgiving holidays and all that other good stuff. And then we have basically another week of classes this week or that week, which is what, the 30th and the 2nd. And then we have another little last set of lectures down in here. And then the finals would be on the 14th. So basically 3 weeks of, let's see, 3 weeks of lecture things left. One of those days, remember, is going to have a little bit of time for us to do your Google Earth little presentation that we talked about for your final project last week. And that way we can get some positive feedback from each other, kind of polish it up, and then do the final presenting on the 14th down there, which is going to be pretty cool, I think. I posted on the modules, so in the class replays, the video I posted was from the Friday section because it did everything, or we did everything. We had the whole week to do, the whole 3 hours to talk about stuff. You guys are still only responsible for that first half of the glaciers thing, but within that video, I would say the first 30 minutes or so is dedicated to me showing folks how to manipulate Google Earth and use Google Earth and add place marks and what types of things we're kind of thinking about. And if you have any questions about that, you can contact me on Canvas, things like that. If you want to, I have office hours with MJC tomorrow from like 10 to 11, 11:20, something like that. I can give you that link if you guys want to pop on, and if you want to ask any questions or anything like that as well. So I'm here to help. Remember, it's not supposed to be a daunting chore or anything. It's supposed to be a little bit fun and give you some skills to put in your back pocket that you can use moving forward here. So that's where we're at, which is just mind-blowing. And I know my mind has already started to turn to Turkey and things like that. Oops, let's see here. Oh, okay, yeah. So I'm sorry, somebody just sending me a private message. That's great. That's fine. And if you want, you can share with me some of your final project. Like somebody said, they shared their final project that they have so far, which is great. And I'll take a look at some of those. And remember, this isn't a make or break. If you don't do it exactly right or anything, like you're doomed to failure or anything like that. You're experimenting with it, you're trying with it, and that first positive feedback with a peer feedback will be a pretty good positive experience, I think, for everyone of how to do it. So yeah, I'll get back if you guys message me about that. I'll definitely get back to you and see if you're on the right track or not. Okay. And I'll try to dig up too. So I'm going to try to dig up and anonymize some, what do you call it, tours from the previous semesters and things like that. Basically make copies of them or something so that the person who made them is no longer on it. And you can see some examples of what it looks like. All right. And that's where we'll go from there. And I expect ours are going to be a little bit better because we'll have some of that positive feedback and peer feedback. I keep saying positive, but it's going to be positive peer feedback, and we'll go from there. All righty. So without further ado, I want to do some things today with y'all and have some fun and see what we can see here. So we've talked about glaciers last week, and now we're going to start moving into atmospheric composition, the climate and weather controls. We'll probably talk a little bit about ocean currents and stuff if we can squeeze it in between here and there. We'll just kind of see what happens. But I'm much more about leaving a few things out here and there if we have to, as long as it gets us a deeper understanding. So we're not just trying to memorize stuff, right? I want you guys to be able to leave with functional use of what we're talking about in here. So why is it so hot and dry in the Central Valley during the summer? That's kind of some of what we're going to be heading towards and trying to figure out. And I love Death Valley and jumping off the sand dunes in Death Valley and things like that. If you're once a long jumper, once a track person, you're always a track person, even when your legs get old and ligaments start giving out and things. But that's what we're going to take a look at. So one thing that is really important that I want to show to you about the Geo News for you to Geo knows, Canada right now, British Columbia, Washington, they have had just a fire hose of an atmospheric river pointed at them for the last, about 3 days, 4 days, somewhere in that neighborhood. Some places have gotten over like 20 inches of rain or a little bit more. And British Columbia, remember, has had some really bad forest fires and things this year too. So they've had a huge debris flows and just floods from the massive volumes of water. And what's kind of interesting about this is the same spots that are getting hosed right here are also the same ones that experienced some of the hottest temperature abnormalities in recorded history, right? It was almost 49.5 degrees up there, which Celsius, which is 120. Let me see. Let me do 49.6 degrees Celsius to Fahrenheit. Let's see. I can't 121. There we go. 121.3 degrees Fahrenheit, way far up this north latitude. That's bizarre. That's weird. There was weird high pressure over it, and we'll see why that dictates hot temperatures a little. Oh, gosh dang it. There's a little Fahrenheit right underneath it. I totally missed it. Oh, well. Anyways, good to know it's right. But these extreme temperatures and now extreme rainfalls, this is kind of what we're going to be seeing here with this, what we call climate whiplash, as climates become a little bit more unstable as the Earth keeps warming up. And we'll be talking about that the next 3 weeks or so here. So you can see tropical feed from Hawaii, warm rain falling on top of very high snowpacks already that they had, and it melted some snow and the runoff was just going nuts. And oops, let me give you this. Doggone it, I forgot to make this link go good. There we go. There we go. But just to give you an idea, there's huge amounts of provincial, hey, where'd the video go? I don't know where it went. Anyways, there's huge amounts of British Columbia that are cut off their main highways. So imagine like I-5 or 99, you know, really big arteries here in California. They've been completely washed out. There was about 400 people that had to get rescued by helicopter on the highway because the bridges in front of them and the bridges in back of them all washed out. And so it was just a pretty harrowing experience. Cell phone services are being wiped out, and I wouldn't be surprised if California has some issues like this, you know, going forward. Not this year necessarily, but you know, at some point in the future, we're going to get hit and hosed with a huge atmospheric river like that, like the arc storms, like you guys were thinking about before. All right. So with that being said, here's what we're going to be talking about today. We're going to be looking at some of the composition of the atmosphere. We're going to be doing, I'm going to start out with doing some fun little activities with you that you guys can do at home if you want to. And we'll talk about that in a minute. We'll take a look at the vertical composition of the atmosphere. We'll do a quick sketch with descriptions showing why the atmosphere in the equator is warmer and has more energy than at the poles, because we're going to see that's kind of one of the big driving forces of our weather and our climate on the circulation of the atmosphere. Has to do with the sun angle. You guys will be doing a little breakout with that. We'll talk about infrared radiation and all this stuff on Thursday, all right, down here. So I think we'll probably get through with some of this stuff today, or at least these two, and then the other ones will probably be on Thursday. So to kind of start off here, and because we started a little bit late, I don't think I'm going to have you actually draw this, but I want you to just think about this. All right. I want you to think about, if you're in your room, surrounding, looking around you, if you had magic air glasses. Like imagine you had like AR glasses or some atmosphere, or not atmospheric river, but if you had augmented reality glasses on and you put those on and you could see the molecules all around you, what type of things do you suppose you'd be seeing? What would those air molecules look like? All right, would they be kind of staying still? Would they be moving? Would they be bouncing? What would they look like? All right. And what would they be made out of? That's what I want you to think about. So just take 20 seconds here. You don't have to close your eyes if you don't want, but if you could see air, what would it look like? And the reason we start out with this and having you think about this is, you don't have a quiz question. I took that out when I modified that, so don't worry about that last little one. The thing to think about here is most everybody just ignores air. We don't really think about it because we can't see it, unless it's foggy mornings like it has been, right? The foggy days, that we're very aware of the air, or when it's smoky or there's pollution filled in the air, we can see the particles of air or the particles of pollutants within the air. One thing I like doing is just kind of waving your hand back and forth like this, and you can totally feel the air running between your fingers, right? It's why the little paper fans and things work, because you're moving air past your face and you can feel it. So what would it look like and how would it move? Well, we're going to be talking about that as we move on for the whole rest of the day. All right. And so we're going to do a little experiment too to take a look at it as well. So just to kind of give you a heads up of what is in air, if I had a cubic meter of air, so a box that's basically a meter by a meter by a meter, that's like 3 feet by 3 feet by 3 feet. All right. In that box of air, so this would basically be about the size of your dishwasher. All right. In that box, that size of the dishwasher there, there would be 3.369 times 10 to the 25th molecules of air. And if you write that out, that's how many molecules are in there. That's a lot of darn molecules bouncing around for what looks like nothing, right? It doesn't seem like there's anything in there except, you know, I don't even know, what is this? Hundreds, thousands, millions, billions, trillions. I don't know what comes after that. That's a lot of zeros though, right? So hard to count, but easy to quantify if you take a little bit of chemistry. And within that box, 78% of all these molecules are going to be nitrogen. And notice I say molecules and not atoms. The molecules means they're two atoms bonded together. So in this case, they're two nitrogens bonded together. The oxygen that we breathe in is actually two oxygen atoms bonded together. So we call that an oxygen molecule. So that's the one thing that a lot of folks forget is when you take a deep breath in, 78% of that breath is nitrogen. Only about 21% of that is oxygen. The rest of it is argon, or about 1% of it's argon. And then carbon dioxide's way down there at like 0.04%, but it plays an outsized role in what happens in the atmosphere. And by the way, this is in dry atmosphere, assuming there was no water vapor in there at all. Okay, so this is what the percentages would be. So one of the first things we're going to do is we're going to do some atmospheric pressure challenges. And instead of doing breakouts, here's what I would like you to do. All right. I want you to make a prediction. I want you to make a prediction of what do you think will happen if I take two balloons, or in this case, you'll see I'm going to have two tennis balls. I'm going to have two tennis balls like this, kind of like these two balloons hanging down from strings. From a piece of pipe or something like that. And I am going to blow in between the two balloons here. So I want you to make a guess, and you can put in the chat, you can do things like that. What do you think is going to happen to the balloons when I blow between them? All right, what do you think is going to happen? So anybody want to make a guess in the chat of what do you think is going to happen to the balloons if I blow really hard? So I'm going to blow a hard puff between the balloons. What do you think is going to happen to them? You can put it in the chat. You can say it if you want. It's up to you guys. But somebody's got to make a prediction. Somebody's got to go out on a limb here. And it's okay. I mean, there's no right or wrong, right? Well, this is just some ideas. Okay, so somebody says they're going to pull apart with a question mark. So maybe not quite 100% sure if that's going to happen. All right. Ooh, maybe they're going to bump into each other. Interesting. So I wonder why. They'll swing in the direction of the arrow. Oh, okay. So that's pull away from each other. So we got a lot of them. They're saying they're going to like blow apart, right? So let's see what actually happens. And so here we go. And I forgot when I made this video last year, it was in my office at an elementary school, and the bell went off. So you'll hear a bell in there every once in a while. So let's see what actually happens. And then we're going to try to draw a little depiction to explain what in the heck happened here. All right. Oops, let me turn on my sound, share my sound here. Sorry. There we go. Okay. Two Bernoulli tennis balls here, and I'm gonna make them so they don't move too fast, and I'm gonna blow pretty quickly between them. Let's see what happens. That what you expected? So it's easier with balloons if you can find them laying around your house. I didn't have any, so we used tennis balls. Yeah, so there's the ring, right? So that was the initial thing here. What happened is, sure enough, the initial response to the balls were to smash together. And it really works a lot better with balloons. You don't have to blow quite as hard because they don't have as much mass, but they donked together there. So let's figure out why they donked together. So let me open up my little drawing app here and then share my other screen. Oops, let me see here. I think this will work now, hopefully. I don't know why the conflict was so bad, or oops, doggone it. Sorry. Oh, hey, all right. Yay. Oh, I gotta make sure I go to the mouse. There we go. Oops, wrong one. Oh, not the wrong one, but just need a new page. Okay, so here's what I'm gonna do. I'm gonna draw, I'm gonna use kind of a big line right here. And here is my bar. Here's my two balloon lines. And I'm gonna say, we'll use tennis balls, I guess, here. Right, so I wanna give you a before. And this is going to help us out and understand. The reason we need to kind of look at this and try to visualize what's happening with these air molecules is because this is what dictates in the atmospheric circulation around us. So if we can kind of start imagining and envisioning the invisible, right, by making a model like this, hopefully we'll be able to kind of envision it in the bigger picture, the bigger scheme of things a little bit later on. So I'm going to use, well, I guess, oops, come on, there we go. Hopefully you guys can see like these little air molecules. So here's air. And what's kind of funny, and what I didn't really draw really much, is that these air molecules are not just stagnant, all right? They're not just stagnant. They are constantly at random, moving all around, bouncing all around, zinging back and forth. Let me see. So let me just, I'm going to put a few arrows on here so you guys can see that they're just bouncing all over the place. They'll bounce into each other, and it's like pool balls, right? Billiard balls, or they'll bounce and bonk off all different directions here. Okay. But what the other thing is that I want you to notice here is that there's pretty much an equal amount of air molecules everywhere, in between the balls, around the balls, on top of the balls. They're just trying to fill in all of that empty space. And what's kind of interesting is all of these molecules, right? They have mass. And so when they're bouncing into things, they exert a force, just like you and I have mass. If I were to run and bump into you and shove you, you're going to be moved, right? You're going to get out of the way. Or if you're, let's say, holding up, and this would be a dirty trick, but let's say you're holding up a whole bunch of plates or something like that on your hands, you know, holding them up like this, and then somebody came and tackled you from the side and knocked you out of the way, all those plates are eventually going to crash down, and because you've moved it, you're not exerting that force anymore. So we're going to try to do something very similar to that, or represent something similar to that with this little diagram here. So here's our before. All right, things are moving around. And then for our after, oops, let me see here. For our after, let's see here. Oops, wrong one. That's what I'm looking for. So for after, I'm not trying to repeat myself, I promise, but I do sometimes. This is what it ended up looking like. And so the reason it ended up looking like this, and the reason we had this motion where the tennis balls were kind of clonking together here, is because when I blew, so I'm going to use, let's see here. When I blew the air through the two tennis balls here, what happens is, maybe if I can get this, sorry. Where we go, there we go. What happens here now is we've taken some of these air molecules, and let me choose a different size, sorry. We've taken some of these air molecules that were here and that were exerting force. So let me doggone it, let me go back to this one I forgot to draw. So it's these air molecules in here are exerting force kind of all around in equal directions around the tennis balls here. That's what I forgot to mention, right? So you have this force kind of acting in all directions on these tennis balls. The air molecules are bouncing around from all directions, hitting that force like this. They have equal forces everywhere. But when I blew through them over on the right side, so this will be the after, when I blew through them over here, now what happens is you're taking these forces that were pretty equal on either side. And now all of a sudden, because there's fewer air molecules in between them, the forces on the outside far outweigh the forces in the middle. So you're basically making an area of low pressure. When you blow through there, you're removing the air molecules from in between them, and it allows the tennis balls, the air pressure on the outside of the tennis balls, to exert more pressure than what's happening on the inside. So I'm going to say higher pressure out here. All right. And then in the middle, I'm going to say lower pressure. So I'm going to use kind of a jaggedy line right there. So there's lower pressure in between, higher pressure on the outside, and that allows these tennis balls to come together. And we're going to see this concept of higher and lower pressures here is really a big deal with atmosphere. And so I want you to be able to try to envision and see what's happening with that. So let me go back to my other screen, and we're going to do one last other cool trick. And by the way, I mean, I can tell you here, it's just physics, right? The ability for how air moves and things like that. This is also how, when I was in college, I made a little bit of side money. Is, you know, you bet people with like, oh, I bet you can't, I bet you can't blow these tennis balls apart, or I bet you can't, you know, well, for this one, I bet you can't blow this piece of paper off of these books. And you always have a lot of people that say, oh yeah, and yeah, I can, no problem. It's totally easy. So here's how you set this up. If you have 3 books, or it doesn't have to be 3, but just a couple of textbooks, the thicker they are, the better. And then you take a piece of regular flat printer paper like this, right? Just taking that, oops, can't see, just a regular printer paper like there, and you lay it over the top. The challenge is to try to blow the paper off of the books. Now, this only works 99.9% of the time if the paper is completely on the books and there's no overhanging pieces of paper or anything like that. But it's darn near impossible. It's darn near impossible to blow this paper off. So here's what I want you to think about. Make another prediction here. If I were to blow underneath the paper here where the arrow is going through, what do you think is going to happen to this piece of paper? What do you think the motion of this paper is going to be? If you think about air molecules underneath and air molecules on top, what do you think is going to happen to this paper if I blow underneath here? What do you think is going to happen? You can put it in the chat. You can say it out loud if you want. What do you think is going to happen to that paper if I blow it up? Does it lift up? Ooh, we have a vote for a lift up. I don't know. We should experiment in just a minute. All right, so 1 vote for lift up. Anybody else have any other ideas, or are we all agreed that it's all going to lift up off of the paper here, or off of the books? Anybody confounded here? Maybe the middle will sink down. All right, so we have a middle sinking down. We have it lifting up. Force might make it sink. All righty, so let's see what happens here. And I'll try to do a better job diagramming this after we see it. And you'll see the first one I had here was my mask on, so it's obviously not going to work. And this is not the most, this is not the best setup because you can see I still have some overhanging bits on the paper here. So if you have full on textbooks, that's probably the best thing. But setting it up with about 2-3 inches in between, that's how you want it. All right, so here I have my 2 textbooks, quote unquote, and here's just a regular plain old piece of paper. I'm gonna put it down there like that, and I'm gonna blow down below right here and see what happens. So you can see how effective masks are, right? Face mask works pretty well, right? So wear your face mask when you go out. But if you take it off, then you can do this. So I'm blowing underneath the paper. I know it's kind of hard to tell. On top. Now I'm blowing on top of it. Same thing happens. Underneath, same thing happens. So this is a great way to make, you can get lots of people that are full of bravado and, hey, I bet you can't blow this piece of paper off. And so if it's a good family member trick, if you want something to do on Thanksgiving. So let me show you. Oops, give me a sec here. Let me show you how this works. Oh, come on, there we go. So here's, oh no, I don't want this color. Give me one quick second. And I'm trying to show you the sketches so it helps you maybe draw these sketches as well. Let's see here. Here's a book. We'll just say it's kind of a big book like this. And here's the book pages. Okay, no big deal. Here's another book right over here. And you can see my sketches aren't perfect, and it's okay because it's just a sketch. It's just a model. All righty. And so then I'm gonna use, I think, brown for the paper to go on top here. So there's my paper that's going on top. I'll squiggle it in a little bit so we know it's a solid piece of paper here. And then again, we want to put in some of the molecules underneath it here. So in this case, I'm going to put the air molecules all around it, on top of it, all around, all directions, everywhere. Try to make it equal, right? There's air on top of the books, air on the side of the books, air underneath the books, air on top of it, things like that. Now, before I blow, all right, before I blow, so I'm going to say this is before. Let me draw some better lines here that might help better explain what I was thinking of. Before we blow here, there is an equal force of air pressure pushing down. There's an equal force of air pressure pushing up. There's equal air force pushing this way and that way and underneath the paper and underneath the paper like this. There's just air pushing down equally from all directions. And that has to do with gravity, and it has to do with all of the air molecules bouncing around and smashing in off of each other, okay? So the big thing here is the forces are balanced. And when they're balanced, the paper doesn't move, right? So when they're balanced, you got no moving paper there. That's the big thing to think about. But, and I really need to figure out a way to, copy and paste some of this. But anyways, let me go back to my books here. So on the after effect, then, let's see. Whoop. As you can tell, my drawing skills have faded a little bit in the digital era, but I'll get there. I'll get better. So the after then, what we saw was something that looks like this. Oops, not 2 F's, what the heck? Apparently my spelling is gone as well. All right, so here's the after. Let me get the brown paper here and we'll draw this. And remember, this one went whoop like that and over, and then whoop and down and over. And the reason, remember, this went funky and went down like this was because now we unbalanced the forces. So by blowing the air out from underneath. So let me draw, get a different color here. By blowing the air molecules this way out from underneath, what that means is you have fewer air molecules underneath. So let me get my little, let's go. So maybe there's just a fewer molecules underneath, but there's still a lot more, and it's hard to tell, but there's still a lot more molecules up on top. And so what that does is it leads to an unbalanced force. All right, so I'm going to say fewer air molecules under paper. All right, so we have a fewer air molecules under the paper like this, which leads to unbalanced forces. And so when that leads to unbalanced forces, what that would look like if we were drawing like physics vectors and things like that, it would look something like this. So you still have the pretty long arrows coming in from the top, right? That same force is existing from the top and from the side. But when you blow the air molecules out from underneath, now you have much smaller arrows pushing up. And so these bigger arrows on the top, these bigger forces pushing down, are going to outweigh and overwhelm what little force from the molecules there are underneath to push up. Because as you blow through, you're literally removing temporarily some of those air molecules from underneath it, which allows the pressure to drop, and the higher pressure on top. I'm going to put higher pressure right here. And then underneath, I'm going to put low pressure here. Okay, so you have the higher pressure on top, lower pressure underneath, which causes the paper to bow down and bow down. And so air pressure is a pretty amazing thing like this. It's a pretty cool deal. And this is one of your sketch notes things, is like sketching one of these befores and afters. It's a pretty cool thing I think you'll be able to do. And I want you to just imagine these arrows, imagine these air molecules as we move forward now, as we start trying to explain some of the other things that, or the atmosphere, I guess, on a larger scale at a global scale. And I just do want to show you one other one. I don't have any 2-liter bottles, but I'm sure a lot of folks will have like even a little water bottle and things like this work, but I don't have a video for it. I want you guys to try this one on your own if you want. Any narrow necked bottle, so wine bottles would even work theoretically, you know, or other types of beverage bottles, depending on what you like to drink, as long as it has a narrow neck. And let me get here. Oops, on it. There we go. Hey, there we go. As long as it has a narrow neck and kind of a big volume of air behind it, if you take a little piece of paper and just roll it up into a small ball, like the size of a pea, so, you know, make it so it's about half the size of the opening here, and you just rest it. You lay the bottle on its side and you put the ball right on the lip here, and you blow. And what you're trying to do is blow the ball into the what do you call it? Blow the ball into the bottle right here, and give it a shot at home later on. See what happens. Thanksgiving fun for everyone, and see what happens, and then try to figure out, if you want, what is happening with the air when you do that. Alrighty. So that's kind of that's where we'll end off. But these experiments. So teacher hat here. If we were in person and you were doing these, and we didn't have to worry about blowing COVID on everyone or anything like that, this is a way to at least get people thinking and experiencing air, because it's one of the most taken for granted things, right? We never think about it because it's mostly invisible. And so now we have a way of thinking about it. We have a little bit of a mental model going forward that could help us out here. So a couple of things with this air, right? Like I was saying, the major components of that air is nitrogen. The rest of it's oxygen, argon, a little bit of carbon dioxide. And this amount of carbon dioxide, by the way, is continuously going up. There's much more of it in the atmosphere these days. And then there's a few other things like methane and helium and neon and a few things like that. But for the most part, it's mostly nitrogen, oxygen, and what we really, really care about too is carbon dioxide and methane, because they're greenhouse gases, and we'll talk about that a little bit later on. So one thing that was not listed in here was water vapor, but water vapor is so variable in the atmosphere. We just usually talk about what's in the atmosphere based on dry air. But you can see, like on these earth.nullschool.net maps here, the areas that are in brown, those are very dry areas of air where there's not much evaporated moisture in there. There's not much water vapor, water gas up in here. And the areas that are bluer and really teal and stuff like that, those are going to be more moist air. And for us, this is what we look for. As these things start creeping towards us, we're like, oh, hey, that's what's going to bring rain. Dry air does not bring rain because there's not much to squeeze out of it. So around the globe, on average, up to about 4% of the Earth's air by volume is water vapor. And those are the things that form clouds and precipitation. But as we know, it's not equally distributed and it changes all the time, right? Cloudy days, clear days, things like that. But what's pretty interesting here is water vapor also absorbs heat energy from the Earth as it radiates up, and is pretty good at preventing infrared radiation from escaping. So if we didn't have clouds and we didn't have the atmosphere and we didn't have some of these greenhouse gases, all of the energy that hits the Earth during the day would just fly right back off the Earth, be radiated back out into space at night. And we'd be really cold in the nighttime versus really warm in the daytime. And there'd be huge temperature swings and nothing would be able to live. So a little water vapor, a little carbon dioxide, a little greenhouse gases, keep things in balance. That's good. Too much change, and we're going to see that can lead to some problems. So now the other thing that is in our atmosphere that we tend to overlook are the aerosols. And so aerosols are basically tiny solid or liquid particles, super duper small. And basically what's important about these particles is it allows a spot for water vapor to condense onto. So if we had completely clean, clear air with no particles in it at all, like no pollutants, no dust, no other things like that, it would be really hard for water molecules to condense and make drops to eventually make rain. A little bit of pollutants up in the air, that's natural, right? These aerosols that are in there, that's good for really allowing water vapor and water molecules to condense. But too much obviously is going to lead to some issues in terms of breathing and stuff like that. So aerosols, they can also reflect some sunlight. So think about smoke, wildfire smoke that we've been dealing with in the summers. Those are aerosols. That smoke is aerosol. They have different sizes of particulate matter in there, but hopefully you noticed during the smoky days that it wasn't as bright outside because it was filtering some of the sunlight. It was reflecting some of it before it got to the Earth's surface here. And one of the other things here is those aerosols definitely help color the sunrise and the sunset. And there's a link right here in the yeah, I have a hard time talking, sorry. There's a link in the presentation there that'll take you to the Purple Air website. And basically what the Purple Air website is here, you should see it pop up here. These are sensors that measure in every 10 seconds or so, some cases every second, what is the particulate level in certain areas. And so if it's green, it's generally much nicer air. And if it's like purple over here, this is probably next to a fireplace or something like that, where there's some smoke pumping out. But in the springtime, or not in the springtime, but in the summertime when there's wildfires, all of these are like red and not so great. So cleaner air is where it's green. My guess is the higher numbers right here, these odd ones out, probably next to some people burning wood stoves and things like that, and the air hasn't mixed. But you'll notice our air quality is still pretty high up, right? It's not super great, especially down in Fresno, it's not super great. And we're gonna see that it's hard for the air in the valley to mix around. And you can see, look at LA. LA is pretty impacted too. They've had some really high pressure where air is not moving and all the pollutants from the cars and junk like that is building up over time and not moving out. Same thing happens in the valley, but today we're getting a little bit of a breeze that is starting to mix things out and get that air circulating and moving around, right? So here's a picture just of what those pollutants can look like visibly, right? This is from the Camp Fire in 2018 that destroyed the town of Paradise in Northern California. And you can just see how those smoke particles went all over California And really, it wasn't a huge fire. It just was super deadly and super damaging because it went through a huge community, and put up, when it burned, it put up a lot of aerosols that would come into here. All righty. So that's kind of what these aerosols look like, and that's what's in our air. So when we're thinking of air, think of the invisible, right? The nitrogen, the oxygen, argon, carbon dioxide. We can't see those. Think of the water vapor, and then also think of some of those pollutants that are not pollutants, but aerosols, things that are floating around in there. These also include viruses and bacteria and all sorts of other things too, which is why, masks are so effective at preventing a lot of these transmissions of, you blowing stuff out. Or if you wear a mask that's N95 is small enough, it will filter out a lot of these aerosols and make it a much higher chance of you breathing clean air and not viruses getting through, or bacteria, or things like that. All righty. So when we talk about that vertical structure of the atmosphere, then, so we talked about what it's made out of, but if you were to take a chunk of air like this, or what I like to think of is taking like a 1-inch piece of PVC pipe. So think about if you've ever done sprinklers or anything like that, or you've seen sprinkler lines put in, some of the bigger lines they put in are about 1 inch in diameter. Now, if you had a PVC pipe that could stretch from the bottom of the earth all the way up to the edge of the atmosphere, and you could look at the amount of molecules in it, this would be kind of a good way of imagining it. Down near the surface, there's way many more air molecules down at the surface because of gravity, right? Gravity is going to hold these things that all have mass on them. They're going to hold much more of them near the surface of the earth. And as you go up higher, as the air kind of rises because of whether it gets hotter or colder and causes density to change, as you go up higher in this air column, you can see the amount of air molecules becomes less and less. The density of the air becomes less and less the higher you go up. So if this was an imaginary PVC pipe and I was right at sea level, or just about right at sea level, and I capped off that huge, 63-mile long PVC pipe that's 1 inch in diameter here, and I were to measure the weight of all of that air that was in that pipe, all those air molecules would weigh 14.7 pounds down at the surface of the earth, right? So what's kind of interesting to think about is for every square inch on earth, so here's a square inch between my fingers right there. If you were to draw 1 inch square on your table, there would be, because when you're sea level, there's about 14.5 pounds of air weighing down on that. And like, man, 14.5 pounds, that's like, that would be 2 gallons of milk, right? It doesn't feel like that. It doesn't feel that bad. But remember, it's not only just air pushing down. We have, because of gravity and allowing, because gravity pulls the air down and allows the air molecules to act in all directions, we have air pressures pushing up. We have air molecules pushing down in all directions, and those forces balance. And so since all those forces balance, it doesn't make it harder to move in any one direction than another. Now, this changes if you start going like 65 miles an hour in a car, right? And you roll down your window and you stick your hand out the door going 65 miles an hour, right? Your hand is going to get like taken off. Not really, but it'll get taken pretty good. And that's because you're running into all these dense air molecules down there. You're changing the amount of pressure because you're going into it at 65 miles an hour. But if it was just standing there, not much would happen. And so I'm going to make a video tonight when my kid gets home, and he'll like making a video with me, but we're going to karate chop a pencil using nothing but air molecules to hold it down. And you'll see, it's pretty cool. You guys will like it, I think. All right, so anyways, the vertical structure of the atmosphere, like I was telling you, the amount of air changes from higher to lower, the density changes. And what that also changes is the pressure, the amount of weight you feel of air on top of you. All right, so the pressure is basically the weight of the air above you. And so something that's kind of interesting to think about is like, here's Mount Everest. So here's Mount Everest. When people climb all the way to the top of Mount Everest up here, it's 29,000 feet above sea level. Look at that. they are already almost, they've way crossed the 50% of the atmosphere in terms of that. That's why they have to bring so much oxygen when they hike up to the top of Mount Everest, is because half of the Earth's atmosphere is, lower than 3.5, we call it 3.5 miles in altitude. So even if you go climbing Mount Whitney in California is like 14,000 feet in elevation. If you right about here, almost half of the oxygen, half of the air is below you, and you have, the rest of the air molecules above you are going to be really thinned out and not very dense at all. This is why if you go hiking in the mountains, you're taking a deep breath, you have to breathe heavier, and some people get lightheaded because there's literally half the amount of oxygen if you're up way high up here like this. And there's some folks down that live in the equator, in the Andes, in the Tibetan plateau, where that's their whole life, is above this 50% of the atmosphere. So their bodies have adapted over time to better breathe with less oxygen. If you're sea level dwellers and go up that high and you're not used to it, a lot of folks get altitude sickness, or they can't think very well, and they get super bad headaches and things like that. So it's just something to think about here. All right, so about 90% of the atmosphere is below 10 miles. So if you go up in 10 miles in altitude right here, 90% of the atmosphere is there. To get to outer space, technically you have to go up about 60 miles. All right, that's kind of the official threshold of leaving the atmosphere, is about 60 miles up. So how is this all laid out here? How is this vertical structure of the atmosphere all laid out? Well, there's basically, it's based on temperature changes. And what's kind of funky is, you'll notice on the right-hand side here, we have the height on the miles on this side, height in kilometers on this side. And down here, we have the temperature. So this red line is basically following the temperature as we go up in elevation through the atmosphere. And what's kind of cool is we have all these weather balloons that get launched every day around the world, and in the United States as well. But those weather balloons go up and they record the temperature, the pressure, the humidity, all these different things. Now they automatically send to the computers, but back in the olden days, they'd have to go track those suckers down and try to figure out what the readings were in them. And then these are what get put into weather models to help us understand and predict what we think the weather systems are going to do. But they have all this invaluable data that helps us track the changes. So in the troposphere, so we have the bottom layer of the atmosphere here, it's called the troposphere, and I'll give you some more breakdowns of this a little bit later on. This is where all the weather is. This is where all the weather happens. It's where all the clouds are. You basically go above the troposphere into the stratosphere. And by the way, there's a barrier line there called the tropopause, where the troposphere ends and the stratosphere begins. When you go up into the stratosphere, there's like no cloud, or there's very few clouds. There's not much water, vapor, or moisture, or anything up there. Most of it is all in the troposphere, in this very thin layer next to the Earth's surface. But the thing I want you to notice here is, as I go up in elevation, look at the temperature. It starts out at 16 degrees Celsius, or like 60 some degrees Fahrenheit on average around the globe. And the higher up I go, by the time I get over to here, about 10 kilometers up, we're at minus 60 degrees Fahrenheit, right? Minus 70 degrees Fahrenheit, somewhere in that neighborhood. So it gets colder the higher up you go here. And the reason it gets colder is, as the Earth radiates its heat, right, it absorbs energy from the sun, the ground heats up and heats the air above it. As that warm air kind of moves up and away, it exerts energy, right? The moving up and expanding and getting bigger causes it to cool down. It loses some of its energy. And as it loses its energy and it loses its vibrations, the molecules lose their vibration amounts, they cool down. That's what temperature is. So it cools down the higher up we go. And then check this out, we hit the stratosphere. And the reason we call it a new layer and the stratosphere here is, look at the temperature. The temperature all of a sudden, the higher up you go here, starts increasing. And it increases because of the ozone layer. We have the ozone layer up there, which I'll show you a little bit later on, is O3. And it's what filters out infrared radiation, not infrared, ultraviolet radiation, sorry, UV rays, most of the UV rays and things like that. It gets absorbed in here. And that extra absorption of the energy from the sun causes them to move around even faster and gets warmed up again. So they warm up, warm up, and then they hit that stratopause. And once they get above that, they start cooling down again. This is where you see meteors burn up and things like that. And then you get into the thermosphere, where you get more charged particles interacting with solar energy from the sun, and it causes it to warm up even higher. The thing is here, though, there's so few molecules up there that you wouldn't really feel hot. Even though it's pretty warm up there, you wouldn't feel warm because there's not enough molecules bouncing off of you to impart their energy to make it feel hot or to feel warm. You just wouldn't even hardly notice it. But you can measure it, it just wouldn't be super noticeable. All right, so troposphere, like I was saying, bottom layer, it's where we live. That's where all the weather happens, all that good stuff. It cools, here's something to know, it cools about 3.5 degrees Fahrenheit for every 1,000 feet you go up. So we'll be looking at this next week when we talk about, why is it so cool in like Sonora Pass or something like that in the mountains in the summertime when it's 100 degrees here. That's some of the things we're going to be taking a look at. All right, so there's our stratosphere. Like I said, it absorbs all that ultraviolet radiation. And then the outer layer of the outer boundary of it's called the stratopause, and then you go into the mesosphere. And within that stratosphere, what I just wanted to make mention here again is that's where the ozone layer is. And just to kind of give you a little bit of hope and a little bit of, like rah for trying to battle climate change here, is in the 70s, man, people came together in the late 70s, early 80s. People started realizing that our ozone layer was depleting, and they found this huge ozone hole down at the bottom of Antarctica. Really couldn't think of that. Down at the bottom of Antarctica, and they realized that there were some special chemicals called chlorofluorocarbons, the CFCs, that came out of like old hairspray cans and air conditioning units and things like that. And they would get up into the atmosphere and actually destroy the ozone, the O3 oxygen. And then because they're what we call free radicals, they could go on after they destroyed one ozone molecule, they could go on and destroy another one without even getting broken up. So we realized we had to cut that out. We had to stop producing these CFCs in hopes of trying to make the ozone hole start disappearing, or not disappearing, but sealing back up. And the reason we don't want a hole in the ozone layer is it allows ultraviolet rays in. And if that allows extra ultraviolet rays in, then skin cancers will go up. It's not going to be healthy for humankind. And the way the physics works, most of it hangs out. The ozone hole hangs out mostly in the southern poles, the South Pole over Antarctica. And in the early 80s, we were able to come together and create something called the Montreal Protocol, which banned CFCs. And the hope in what we're starting to see, even though this one doesn't show it quite well, is that the ozone layer, or the ozone hole, is starting to get a little bit smaller, or had been getting a lot smaller, and was healing itself. It's going to take a few decades for all those CFCs to kind of wear themselves out and fall out of the atmosphere. But hopefully in like 20, 30 years from now, this will be mostly completely sealed up, assuming people don't emit more bad stuff into the atmosphere to destroy that. But the goal here is, or the moral of the story is, people can come together and they can solve world problems. And we'll see how they tried to do that with climate change this past week when we study it in a week or so. All right, so there's the thermosphere. So last thing, here's what we're going to do. We are going to end on a 10 or 11 minute long little breakout room here. So let me get you a couple of, let me get you this. Gosh darn it. I'm going to show you how to use this in just a second, and then let me get the breakout room open because I had to close that when I restarted. It's actually breakout number 1. I don't know why I called it breakout number 2. Because I can't think straight. My brain is a little jello-y these days. I don't know about you guys. Oops, sorry. That was just to one person. There we go. This one's to everyone. All right, so here's a Jamboard. And when you open up this Jamboard here, in the background, you'll see this screenshot. So this doesn't do anything. This is just a background image, all right? But here's your directions. You're basically going to open up this Earth-Sun simulator here, And you're going to play around with this app for a couple minutes. And I'll show you how to use it just really quickly here. And I just want you to record some things that you notice and wonder here. All right. So what are some things you notice and wonder as you play around and manipulate this thing? Then it says move to the geographic point to an area near where you live. And I'll show you how to do that. What do you notice? What do you wonder? You're going to be able to play with some times and things like that. And then there's another question over here. We'll see if we have time to get to it, but it's like, what time of year has the most direct sunlight? So that means the blue line that you see right here is going to be closest to straight down from an observer that's down at the bottom over here. So let me show you how this works and what it looks like. It's a pretty awesome simulator. It loads pretty doggone quickly. All right. And this is kind of what you'll get to begin with. On the right-hand side, I'm not going to show you everything, but on the right-hand side, you'll notice if I pull this thing down, it changes the time of year. That's how that works. Okay. So you can go there, change the time of year. If you want to change the time of day for each one, you click where it's the little clock down here where it says time of day, and you can see how the day changes as you go through like this. That's one thing that you can do. If you want to find your own spot, I think this is how you do it. You go to use your location and you can click on that and it'll take you over to where we are. You can also shift this up and down by using the slider bars to choose different points in the earth. So that's the first little bit. All right. And then down here, you'll notice we have something that says sunbeam. So you can see, hey, this is where the sun angle is coming in. You can turn all these things on if you need to, but you don't need to. You can put on the different labels, see why those are there, try to figure out why that's there. And then the last cool thing that you might want to goof around with is the heliocentric view. And so if you click on the heliocentric view, it gives you everything that you can see. And as you go around there and you play this and you make it go, you can click play like this. And you can speed that up, but you can see how this changes over time. So I'm going to cut you loose, just make some notices and wonders. This will probably, we only got about 10 or 11 minutes to do this part here. But just what do you notice? What do you wonder? There's so much to play with. I mean, you could spend hours on this and never see enough. But I just want you to have a chance to experiment and play around with this before we move on. All righty, so I'm going to put you into breakout groups here. You have all the links. I think you'll be good to go. Just goof around with it. You can't break it. You can always reload it and reset it or anything like that. There's nothing that you can do to break it, so don't worry about that. And let me put you into breakout rooms. So do me a favor, please, like talk with each other. You know, you can share screens with one another, but don't try to be an active participant, I guess, is what I'm trying to say here. All righty. And contribute some good conversations to what y'all are doing. So I'll do 4 breakout rooms. That way you can have groups of 3 and 4, and then we'll go from there. All righty. So we'll do 10 minutes or so and see how many you can get in 10 minutes. All right. Welcome back. Man, great job. I know 10 minutes is just scratching the surface on this thing, but you have the link if you want to goof around on it on your own. I just realized that you can change the animation speed and things like that and just make it go bonkers going around the earth here. So we're going to end up taking some of this information that you're looking at here today and some of your notices and wonders, and we're going to try to figure out how does that then affect heating differentials on Earth. And how does that heating then affect the actual movement of the atmosphere and moving around? So it turns out that, the hotter air is, it becomes less dense, it starts rising, and that starts causing convection currents to occur. And that's what starts getting the air moving everywhere. Which is kind of cool and interesting, and we'll hopefully be able to better understand what then controls our weather and our climate by the end of Thursday here. All righty, so that's where we're going to end for the day, for the afternoon. Great job with that. I got to look at all of your awesome notices and wonders here, and we'll come back to those when we have a little bit more time on Thursday and talk about them. But in the meantime, have a great Tuesday afternoon. Hopefully the winds will start blowing some of the fog and the overcast and all that stuff away. And on Thursday, if it looks like we'll have good air, or not good air, but good viewing, I'll tell you about a lunar eclipse Friday night. It's one of the longer lunar eclipses of a long time, actually. It's like a 3-hour long lunar eclipse in Friday night, right? Late Friday night. So we'll talk about that on Thursday. So that's all I got for right now. I hope you guys have a good afternoon, and I'll see you all on Thursday. All righty. See you later.